Okay, well, first, let me thank the organizers for inviting me. So what I'm going to talk about is, at this point in time, probably everybody has played around with one of these large language models, like ChatGPT, for example. And so I want to talk about what is the mathematical structure, or at least part of the mathematical structure that has been computed by these models. And so let me first remind you like how they work on a very abstract level. So on a very abstract level, you just take sequences of symbols, which is just words, and the machine predicts for that the probability of next symbol. So the probability of any next word, the complete probability distribution of all the possible next words, and it's driven. So it's rewarded when the probability of the next, the highest, the word with the highest probability is the one that's in the actual text. Okay, so you don't actually compute any probabilities from actual texts, because that would be sort of vanishingly small for any reasonably large sentence. But the machine produces the probabilities, and then in this way it has to be in agreement. And then when it's sort of optimized that task, then you say it's trained, and then you use it, and then you can have a conversation with it. Okay, so somehow it understands. It has found a way to encode what we understand as meaning. So the question. So I want to break up the problem in two parts. The first part is what is the mathematical structure on the data, which is just sequences of symbols and probability of next symbol. The other part is what's happening with the neural network and how the neural network is able to learn that. I'm not going to say much about that. That's sort of a different story for the moment. I'm just going to talk about what is the structure that's encoded by the sequences of symbols and probability of next symbol, and sort of also try to think about what the structure that encodes meaning and in what way this could happen. And when I say meaning, I just want to have a very practical approach to meaning. I would say that meaning is something which is preserved by translation. So somehow we're able to communicate through translation, and so something must be preserved, and we kind of understand that whatever is preserved, that's the meaning. And so mathematically, we could also try to organize it this way. Okay. All right. So first, of course, it's about continuations of texts, and this is a very old principle in semantics. So semantics. So let me apologize, by the way, to some people who have already heard some of that stuff. Okay, so in semantics, basically, it's a well-known principle. It's called distributional semantics, that if you know the statistics of some text, then it will tell you something about its meaning. And in particular, if texts appear in similar environments, then they have similar meanings. So how do we mathematically express this? Well, the idea to mathematically express, of course, there's two obvious ways. One of them is to think of language as a poset. And you can say that one expression is less than or equal to another when the second expression contains the first. So for example, red is less than or equal to red rose. And that is a poset. Because if you have red less than or equal to red rose, and red rose less than or equal to red rose smells nice, then red is less than or equal to red rose smells nice. So you have associativity, this property that we need for posets. Okay, so and you can do poset in one direction or in two directions. So you can say that red is less than or equal to pretty red rose also. So you can do this on the left. But most of the stuff I'm going to talk about work for both orders. And actually, the LLMs use for the most part, they use the order of extending in one side. So we can keep this in mind. So from that point of view, if you want somehow encode, say that the meaning of red, say, is encoded in all the expressions that contain red, well, from this point of view, it just means take the principal upper set generated by red. So it's just the poset, and therefore you can think of the principal upper set. On the other hand, people also very often in the past thought about language as a monoid, and that's great. So of course it's the same idea. You can take the right monoid generated by ideal generated by red, which would be everything because the monoid operation, of course, is just concatenation in this sense. So in this case, red rose would be the result of multiplying red and rose. So in both cases, you have some sort of ideals or filters. You can take everything that contains a particular text, or everything which is contained in that text. So the dual ways of, you can take the principal upper set or the principal lower set, in other words. But now all these things are missing one key point, which is the probabilities, right? So it's important actually to have these numbers, not just 0, 1, not just Booleans, because the machine is actually trained as a gradient descent. So therefore, you have to have something smooth. Okay. Yeah. And so from the point of view of category, because everything I'm going to say has many different explanations. Some of them are from just metric spaces. Some of them are from category theory. And so from the point of view of category theory, an ideal is called a presheaf, and a filter is called a co-presheaf. So we'll see that. Okay. Yeah, this is just what I just said. So in either case, if you take the upper sets or the lower sets, you construct a completion of the poset that you started with. And that's sort of the general case in category theory also. Yeah, so this is the principle of distributional semantics, and basically that's what we're going to apply. And just to remind you, space of ideals is usually a very good object to play in if you have some algebraic situation. For example, if you have commutative algebra, the space of ideals is a spec. So you can think of the algebra as an algebra of functions on this space of ideals. And we can keep in mind that maybe in some sense we can think of algebra of language as an algebra, and we can try to think about what would be the space of ideals. Of course, it will not be such a nice geometrical object as in commutative algebras, because we're in a no commutative world. But we can try to think about this, and we can see several things about it. So these are the questions that we're going to try to answer. And so let me say that this is joint work with Stéphane Gobert. Some of what I'm going to say is also joined with so this is this paper that you can see. You can find this stuff I'm going to talk about. Some of that is not there. It's sort of a continuation of this also with Matthew Trager, which is in Amazon AI research. And the previous work where this started was with Ty Bradley and John Terilla. And so we wrote that paper in this sort of categorical language. But then we decided, in the paper with Stéphane, we said, okay, well, let's not use a categorical language, because maybe it will be more easy for people to understand if we just use metric spaces and polyhedra. And there were some related experiments from this group in Amazon AI that you can see. Okay, so I'm going to, okay, with contents it doesn't matter. We're just going to go through it. Okay, so what I'm going to call a probabilistic language model is basically, you can think of the poset of language just as I described it, where text is less than or equal to a subtext. And we have some collection of text. It's actually reasonable to think that this poset is just a free monoid generated by some words. And then, because we don't want necessarily this to be infinite, we can of course grade it by the length of the text. And then we have to make sure that everything we do is compatible with this grading. And it is actually. But the basic ingredient is some probability function. It doesn't necessarily have to be normalized. So it's some function that takes two elements of the poset and spits out a number between 0 and 1 or between 0 and infinity. But the main thing we're going to ask is that if you have AI less than AJ less than AK, then the probabilities multiply, just like conditional probabilities multiply. And that's reasonable. That's actually the assumption that people make in LLMs, because when you introduce a prompt, the machine produces a probability distribution, it samples from the probability distribution, then it takes the sampled word, puts it back into the text, do the same thing again, so the probabilities multiply. So that's the central property. And by the way, I just recently realized that you can also think of this as P, this probability function, being an element of the incident algebra. I think it's called the incident algebra of the poset. Okay, and that's actually a very, very reasonable way to think about it, and it leads to nice things. But in here we didn't think about it this way. Instead, we thought about that this is actually secretly a directed metric space. So what is a directed metric space? Directed metric space is a set with a sort of distance function that doesn't have to be symmetric. That's the whole point about being directed. And actually takes values in minus infinity, infinity. But the fundamental thing is that it has to satisfy the triangular inequality, and the distance of anything to itself is 0. And then the first thing to notice is that what we defined as a probabilistic language model is actually just such a directed metric space. Okay, and so you have basically this space of text, and then you take the distance to be minus log of probability if AI is less than or equal to AJ, the probability of extension, or you take the distance to be infinite if the probability is 0, so minus log of 0 basically. And then what you notice is that this map satisfies the triangular inequality. Okay, it satisfies the triangular inequality on the nose as an equality. It saturates it if AI is less than AJ, less than AK. Or if AI is not in AK, then both sides of the equation are going to be infinite. But it's possible, for example, that AI is in AK and AI is not in AJ. So, you know, in these cases, where at least one of the elements is infinity, it would be satisfied not as a saturated inequality, but as an actual inequality. But overall, you can check that it's satisfied. And in fact, actually, it fully recovers the poset because it only, you can say that three things are, in the form AI less than AJ less than AK, if and only if the triangular inequality is saturated. Okay. And for those of you who like categories, let me just point out that this is a category also enriched over the monoidal closed category minus infinity, infinity. And that's a very simple thing. And this is was noticed by Laver back in the 70s, that metric spaces are categories, enriched categories. And what does that mean? It means that, you know, usually if you have a category, the home between two objects is a set. Well, here it's an element of some other monoidal category. The monoidal category is extremely simple. It's just minus infinity, infinity. And when you compose morphisms, you just multiply them in this monoidal category. And then when you want the fundamental axiom of, oh, can I use this? Yeah. Here, of composition of morphisms, it just means that Dij plus Djk is greater than or equal to Dik, because the categorical structure in minus infinity, infinity is just the opposite of the usual order of numbers. Okay, and you take it to be the opposite of the usual order of numbers because you want it to be the usual order in 0, 1, or in 0, infinity. Okay, so this is just a metric space, but it's also a category. And the first thing we'll do is if you come from a categorical point of view, you want to immediately think about presheaves, or sheaves if you have a topology, but for the moment just presheaves. And this turns out to be just a polyhedron. So you can compute this presheaves. And it just turns out to be this nice directed polyhedron, which is defined, so if you have n elements, n texts, these are n vectors. They can take the value infinity, but not all of them. And the equation is actually, oops, sorry. Yeah, so this equation here, xi less than or equal to xj plus dij, of course it comes from the metric space point of view. But let me also notice that it's so-called alcove polytope. Okay, Maxime talked about that as a special case of something.
Inequalities with less than 0, bigger than 0, no opinion. And here we got arbitrary numbers.
What is the inequalities?
No, in alcoves,
yeah,
or chambers, you have this. There's no constant terms, 0.
Oh, in both that? No, I think I think you can have constant term.
Central polytopes, yeah.
Okay, I think you can have constant term on the left and on the right. You can have like you dot with the roots. You dot with the root ei minus j, and then you want this to be somehow between these two numbers.
No.
Oh, okay. Well, there is a story. Okay, all right. Well, anyway, okay. All right. So maybe only in special cases. This is what Maxime was talking about yesterday. So basically, but they're defined by the hyperplanes are actually just orthogonal to the roots, the an of the an root system, ei minus j. You can see this just says that xi minus xj less than dij. And you use the matrix dij for one and the matrix dji, the transpose matrix, for the other. Okay. And so the first thing to notice about this is geometric meaning is that actually they are just spaces of non-expansive functions. Okay, you can just put this metric d on L, or d transpose, and on minus infinity, infinity, you can put, oh, I forgot to mention the metric. So there's a metric on this polyhedra, and this metric is called the Funk metric, or the Max metric. So it's just the maximum of all the differences for all xi not equal to infinity. Yeah, so this is a sort of non-symmetric metric, which appears actually, it's a classical object. It's very much related to Hilbert metrics and things like that. So we'll see in a second also. Okay, so you can extend this definition to the case of R. Then you have to extend your coefficients a little bit because you know, sometimes the second coordinate has to be infinity, and then the maximum of empty set is minus infinity. So this is the right convention. So you can see that immediately that if you have this condition for non-expansive maps, this says precisely that xi minus xj is less than or equal to dij. So these are just non-expansive maps. And categorically, it's the category of presheaves. So in other words, you take functors from your category to your category that you're enriching over. Okay. So this is the category of presheaves, and the category of co-presheaves is p hat L. Okay. And the first thing you do when you have a category and it's presheaves, of course, you consider the Yoneda embedding. And in this case, the Yoneda embedding is just to, actually, it's, so basically to any text A, you associate the vector, which is the distance for any other text to that vector, which is, this is y here. Oops, sorry, keep pushing the wrong button. Yeah, this is this guy here. So the distance, so y of ak is the distance from something to ak. And the co-Yoneda embedding is the distance from ak to anything. Okay? Oh, I'm sorry. I went very far ahead, I think. Yeah. Okay, sorry about that. Here we are. Okay. Yeah. So this is what I wanted to show. This is the Yoneda embedding, and it's an isometric embedding with respect to these maps. With respect to the func distance and the distance that's defined on the category, it's an isometric embedding. So that's interesting because, you know, in general, if you have a finite metric space, if you try to put it in the Euclidean space with a Euclidean metric in an isometric way, you cannot do that. There's conditions that have to be satisfied. But here, with this metric, you can make an isometric embedding. And there's the embedding, the distance from that. And people in metric theory also consider this stuff. I think it's called maybe the Kuratowski map or something like this. You know, you take x, the point x, and then you take the distance from the point x that defines a map. Okay. All right. So now the reason actually that this Yoneda embedding was an isometry is because of something called the Yoneda lemma. And the Yoneda lemma just says that the coordinate xi, so x of ai, is just the distance of this Yoneda embedding to x. So basically you should think of this as you're adding sort of ideal points. So the original points are there, but there are also a bunch of other points. And this bunch of other points, so the defining inequalities now for this story, xi less than or equal to xj plus dij, just become sort of the triangular inequality with respect to the metric from this point of view, because xi is the distance from yai to x. So this is kind of a metric closure. Let's say you had this metric space and then you wanted to metrically complete it in some way. You can think of it from this point of view also. So these are triangular inequalities for these maps. Okay. You know, of course, always, whatever I'm going to say, there's always two sides. One is extension, one is the presheaves, and the other is the co-presheaves. One is extensions of text, and the other one is restrictions of the text. Okay, so, all right. And now we can go back, once we went to this comfort place of metric spaces, we can go back to probabilities. And of course, you know, you can go back from probabilities but just by exponentiating this PL, and you end up with this polyhedral cone Q of L. So this is just the exponentiation of e to the minus xi of all elements in P of L. And this is defined by this equation, Zi greater than or equal to probability of aj given ai times J. This is a cone, of course. And actually it turns out to be a sort of generalization of a known object, something called the order polytope. The order polytope is in the case where the probabilities are just either 0 or 1. Just associated to a poset that was defined, or or maybe it was folklore, but definitely defined in a paper by Stanley, and called the order polytope. So in that paper, actually the variables were just totally between 0 and 1. So we have a sort of a cone version of that, basically, but extending in the sense that we also include these probabilities. Okay, and now we can also say that the probabilistic language model, by the way, that what I define probabilistic language model, which we can also think of it as just an element in the incidence algebra of the poset. We can also think of it as a category enriched over 0 infinity. And I'm just translating here the metric axioms, and they mean this, with equality if and only if AI is less than AJ less than AK. And so this Q of L is the category, this cone is the category of presheaves on this category, and the other one is the category of co-presheaves. Okay, so we expect this to be nicer. Now, all of a sudden, instead of having a finite object, we have an object which is continuous. So, yeah, I mean, you can try to think about, so this is what I'm going to say is not precise, but you can try to think about this as sort of the parameters of a neural network that was trying to learn this data. So you think the data is actually discrete, but in reality, secretly, they're not discrete. They live in this continuous space. And we see immediately that these variables come up in this sense. Okay. Yeah, and so it's kind of also interesting to write down the metric using on this Q of L, which is defined by this func metric and is the maximum of the ratios of logarithms. And you recognize that as something related to something called the Hilbert metric, Hilbert projective metric. Okay, so this is the multiplicative version. We talked about all that. And the first thing to note is that actually this unit embedding puts the category inside this polyhedral cone. And what we find, the first thing we find is that it's not just any point, but they're actually extreme arrays of this polyhedral cone. So they go into extreme arrays into of this polyhedral cone, and of course, you know, from this definition, because you by minus log you can go to P of L, you can call this P of L an additive extreme array, because an extreme array, of course, is just array, so it's invariant under scaling. But if you take minus log of that, it's invariant under addition. So you have extreme arrays in the familiar setting of Q of L, but in the setting of P of L, you have this sort of additive extreme arrays. And the reason that this works, of course, is basically because if I have AI less than AJ less than AK, then they satisfy the saturated triangle inequality. And what does that mean? It precisely means that, you know, Y of AK, so here, this is Y of AK evaluated at I, this is Dij, and this is Y of AK evaluated at J, and it basically says that it saturates the inequality is defining the polyhedron. Okay, so that's where this comes from, but this is actually extreme arrays. Okay, so, but now you can also sort of see you can also ask the question, are they the only extreme arrays? And now you can sort of start imagining the answer if you think about what happens if you take the upper set completion of a poset. If you take the upper set completion of a poset, the principal upper sets live there, but there are other upper sets. So here also, it turns out that actually the unit embedding goes into these extreme arrays, but there are other extreme arrays, and the other extreme arrays, they just basically correspond to upper sets or lower sets. Okay, and the way to see that actually, well, I mean, first you have to notice that if you make a small change of variables, this polyhedron actually becomes a little bit more familiar. So if you assume that the empty set, the empty text, is already part of your structure, then you get for any AI less than AJ, you also can put A0, and therefore you get the probability of AJ given AI is the ratio of the probability of AJ by the probability of AI. Okay, so when you have this inequality, you can write it as you can write this factor now as a ratio, and then you can make change of variables. And then the inequality becomes just yi tilde greater than yj tilde. And so by proving some sort of generalization of that, even in the case when A0 is not assumed to be in the set, we can show that what are the other extreme arrays. And of course, A0 being in the set just means that all these probability distributions come from one probability distribution, okay, overall. Okay. All right. So basically, and the theorem is that the vector generates an extreme array if and only if the function that it defines by its coordinates is a positive scalar multiple of the characteristic function of a lower set whose Hasse diagram is connected. Okay, you can take the lower set, take the Hasse diagram, and if it's connected, then it corresponds to one of these extreme arrays. And there's another result for upper sets if you look at the at Q of L. Okay, right. So this is the beginning of understanding what the structure of the space is. Okay, yeah, and of course any connected lower set is generated by its maximal elements. So some of these extreme arrays are generated by a single text, and some other ones are generated by a collection of texts. Okay, now we need to notice another sort of characteristic of this polyhedron, and to do that we have to use tropical geometry. So basically, just to remind you that if you take minus infinity infinity, you consider the min operation, the s plus t to be the min of st, and times to be addition, which basically just means it's a kind of logarithmic version of the usual algebra. But to see that it's logarithmic version, you also, for the addition part, you also need to use this great identity that we love and care for, which is the fact that the minimum of two numbers is minus t log of e to the minus s over t plus e to the minus t over t. So which actually is interesting because it relates whatever construction we're going to have to the Boltzmann distribution, and tells us that if you really have a linear combination in this min plus ring, this min plus algebra, you can write it approximately as a Boltzmann weighted linear combination by using this identity. You can just say that, you know, for small t, the left side is going to be equal to the right side, and you can write this as a sum of Boltzmann weighted terms. And I remind you that if you look at the large language models, or for the most part in any neural network, they use Boltzmann distribution. So basically, when you have some sort of bunch of scores and you try to construct a distribution, the way you do that is by taking the numbers, exponentiating them, and dividing by the sum of them. So the Boltzmann distribution is the standard thing to use. Okay, and we all know that the Boltzmann distribution, of course, maximizes entropy, for fixed energy. Okay, so right. So now, what do we notice? We notice that actually, well, first here. No, sorry. Yeah, the first thing to notice is that the fact that this is a directed metric space, in other words, that dik is the minimum of di is less than or equal to dij plus djk for all j, it means that dik is the minimum of dij plus djk. It's also realized. And then if you look at this equation here, what does it tell you? It tells you if you multiply d by itself in the min plus sense, then you get, again, d. So it just says that d squared is d. Okay, so it just says that this matrix is actually just an idempotent in this min plus sense. Okay, and so this is a projection. And now we go back to our linear space. We don't know it's a linear space yet, but we just think it's some sort of polyhedron. But now when we look at the fixed part of this projection, so we have d min x equals x, that when you write this out, it just says that xi is the minimum of dij plus xj, which is just the same as saying that xi is less than or equal to xj plus dij. In other words, that this point is inside P of L. So what we notice is that this polyhedron is actually just the image of this projection and the fixed part, of course, because it's a projection. So in a sense, it's kind of like a linear space in this sense. And you can say that it's generated by, in a min plus sense, generated by the column vectors of this matrix. Okay. And then if you change from D to D transpose, then you get the row space of this matrix. And then you will get the other P hat L polyhedron. Okay. And then, of course, you can write, that means that you can write any element as, an element x. You can write it as, because it's, the expression of dx equals x, d of x equals x, just says that x is sum of xj times d dash aj. And so you can write any element then, in other words, as a linear combination of these Yoneda embeddings with coefficients xj, which give you distances. So you can express any element of this way. Okay, so now we understand something more about this story. Okay, and the transpose gives you the other guy. All right, so the categorical interpretation of this fact, why should this happen? I mean, we just showed that any presheaf can be written as this mean plus combination of representables. And this basically just, categorically speaking, it means that any presheaf can be written as a co-limit of representable presheafs. And so we just proved that statement here. But interestingly, not any presheaf can be written as a limit of representable presheafs. If you try to look at all those which are limits, that's a much more complicated and definitely non-convex space. Okay. So, and then of course, you know, you're writing down all of this, you can write down the equations for y of ak in terms of y of aj. So in some sense, you can say that the neural network is finding a solution to this huge mean plus linear system, basically. Because whatever these vectors are, they contain the probabilities, they have to satisfy these relations. So that's one way of thinking about this neural network. And then let me notice something which is striking to me, that actually this metric behaves as an inner product. So it behaves as what's called sesquilinear inner product. It's linear in the second variable here, but it's antilinear in the first variable in the sense that, you know, when you take a linear combination, minus lambda comes out, and then the mean becomes max. So secretly, you have basically some sort of linear space with an inner product on it. So it looks much better than what you might imagine at the beginning. But now I want to show you something else. Now, I said at the beginning that there are two ways to think about language, at least. One is as a poset, and the other one is as a monoid. Okay, so now I want to go back to the monoid sense, and I want to show you how this is related to monoids. Okay, so to do that, let's again make the assumption that the empty text is also part of the structure. And let's think about L as being the free monoid on some words. Okay, and so basically then we get again the same observation that if you have AI less than AJ, you can write the probability of AJ given AI as the ratio of two probabilities, the global probability distribution. Okay, so now just consider this one. So now you notice that you can, of course, consider the Yoneda embedding. And we call this bold y, is the y hat. And this is just basically the probability for AI, it sends this to the vector, to the function that takes the probability of extension of AI by any other text. So this is the Yoneda embedding in this sense. Okay. And remember that the max times now, because if we had the min plus span of this vectors being P of L, now if you take exponential of that, e to the minus that, from max times, from min plus, you go to max times. So these guys max times generate the cone QL. Okay, that's trivial if we know the previous one. So now I'm going to ask you to just consider one specific function here. That specific function, this function, let's call it L, is basically the Yoneda embedding of the empty text. So the value of x, the value of L at x is just the probability of x basically, because the probability of extending the empty text to x. So this is just the probability of x, and it's the Yoneda embedding of A0. Okay. Now let's consider, actually it turns out that basically the right thing to do here is not consider just the monoid, but consider the monoid algebra over a certain semi-ring. And the semi-ring is just 0 infinity with max times, okay? So this is the monoid algebra. And remember, like, how do we, what are elements of this guy here? Elements of this guy here, we can think of them in two ways, either as functions from A star to 0 infinity, and then the product is convolution, or you can think of them as formal sums. So if I have such a function, I can use it to write the formal sum, this being the coefficients. Okay, so this is what the elements of this monoid algebra are. Okay, so basically now we see that this L, which is the Yoneda embedding of the empty text, defines an element of this monoid algebra, okay? And now I want you to consider the left regular representation of A star So AI is acting on this L by the left regular representation. So basically AI of L is just by definition L of AIX. Okay. So let's calculate that. So when we calculate L of AIX, we get L of AIX. So this is the extension from, basically this is the probability of AIX. But the probability of AIX here, we can write it as a product of the probabilities of AI times the probability of AIX given AI. So we're using the assumption that we made about this multiplicativity property. And now this is just a number. And this here, this guy here, the probability of AIX given AI, is just the Yoneda embedding of AI evaluated at the AIX. So in other words, this action just takes this one single vector, and the orbit will give you all the other Yoneda embeddings up to this multiple. And then, of course, just remember what you do when you have a group theory and you're trying to make a group representation. If you have a vector, you can take the orbit on a vector space, and this the group is acting. You can take the orbit of that vector, and then you can take the vector space that this orbit generates, and then you get a representation. So then you do the same thing here. Take the orbit of this guy, and you take the space they span over the max time semi-ring, and what it is, because the orbit just gives you the Yoneda embeddings, is just precisely Q hat of L. So this polyhedral cone is now seen to be the representation of this monoid algebra. Okay, so this is a representation of this monoid algebra. So from this point of view, we have a different way of thinking about languages. So we can say that language is just a function inside SA star, the monoid algebra, that has this multiplicativity property. Okay, and then once you have that, you can get the same structure as I had before here. Okay. Okay. All right. Okay. Now let's sort of let me show you a couple of more things about this story. One of them is that there's a kind of duality that's still to be sort of understood sort of more in depth. But there's a duality between extensions of text and restrictions of text. In other words, if you take a specific corpus, then you can imagine that it would be the same kind of information if you take for any text all its extensions, or for any text you take all its restrictions. It doesn't look to be the same. Yes, it doesn't look to be the same, but actually it turns out to be, and this is a non-trivial theorem. So basically what it means is that if you take this matrix D that contains these Yoneda embedding vectors as columns, the ones that are as columns are the restrictions, and the ones which are rows are the extensions. Okay, but now it turns out that there's a theorem in tropical geometry that if you take the column span and the row span, well, they're actually isometric, and not only isometric, but with a linear kind of isometry. I will show you in a second. And you can imagine that this is a kind of, kind of generalization or an analog of the fact that, of course, the row rank and the column rank of a matrix are the same. There are no other invariants there because the only invariant of a vector space is just the dimension. But here we have the following thing. So the easy way to see how they're related, extensions and restrictions, is to notice that if you have this equation here, xi less than or equal to dij plus xj, if you take xj to the other side, you get minus xj less than or equal to dij plus minus xi. In other words, dx equals x if and only if d transpose of minus x is equal to minus x. So you have a way of mapping the rows of x to the rows of to the columns of d to the columns of d transpose. In other words, to the rows of d. But of course, there's a catch. Okay, and the catch is that you have to extend your coefficients, because now your coefficients were in minus infinity open, infinity closed. So now you have to extend from minus infinity open to minus infinity closed. You have to add somehow infinity. And the way to do that, the consistent way to do that, is to preserve. You can do that. This is a completed, use the completed Mil-Plus semi-ring, which is minus infinity included, infinity included. And you can make the assumption that that plus infinity is the absorbing element. Plus infinity was the absorbing element before. Now you could ask yourself, is it plus infinity or minus infinity? But then if you make this choice, then things work. And this is actually a kind of special case of a theorem proved by Stéphane Gobert and Bern-Stuhlfels in different ways and in different situations, which shows that the span actually of the column span and the row span are associated in this way of a tropical matrix. And let me show you exactly what the association is. The association is that there's two inverse maps. B goes from P of L to P hat of L, and A the other way around. Just takes x to minus x and y to minus y. And they form an adjunction with respect to this inner product that I discussed before. Oh, by the way, I forgot to tell you that this inner product, which is also a metric, it's also the home of the category of presheaves. Okay? So because the category of presheaves has the same structure as the original category. The original category, for every two objects, you get a number. The category of presheaves also has the same. And you can compute that this is precisely this number, is this thing. So now if I wanted to define for you an adjunction, an adjunction means that d of ai of ax comma y is d transpose of x comma by. In other words, that d of minus x comma y is d of minus y comma x. And you can check that this is true. So this is an adjunction. So you have an adjunction basically. And these maps are isometries. D of minus x minus y is dt of xy. And they're antilinear. So antilinear means that, you know, that just means that lambda comes out as minus lambda, max becomes min as you would expect, and min becomes max, of course, because it's x goes to minus x. And now, in case you think this is a sort of very benign map, let me notice that multiplicatively, it's just basically zi goes to 1 over zi. Okay, so there's this thing. Okay, so there is some duality. There's this non-trivial way which tells you that the information on extensions, if you have a fixed corpus, I repeat, the information on extensions and the information on restrictions are actually equivalent. Okay. Yeah, and the duality in coordinates I don't need to go by. Let me just give you a small example where we just have like a super trivial example of just the text is red color, say, okay. So from this, we get red color and red color. We get three texts, RC and RC. And it's easier to see just the probabilities directly. And let's say we have the probability, of course, from R to R is 1, from R to C is 0, and let's say that the probability from R to RC is 1/2. And so we have from C to RC is 1/3, and from RC you can only go to yourself. And then if you take minus log, you get these numbers here. So you get this matrix. So let's see what the span of the column span and the row span of this matrix is. So we said already that we know what the extreme arrays correspond to. The extreme arrays correspond to lower sets or upper sets, but connected though. Now, the way we're going to see this picture is, okay, let's look at the polyhedral cone. The polyhedral cone, you can just take a section of it and make a polytope. And then the extreme arrays define vertices. So we should be able to count the number of vertices. So if we look at the connected lower sets, well, there are three. One of them is generated by R, one by C, one by RC that contains RC and RC. But if you take R comma C, then it's not connected. So it does not correspond to an extreme array of Q of L. So in this sense, we have not included the empty text, by the way, right? If you include the empty text, then everything is connected. So we should expect to see three vertices in the section of Q of L. But in Q hat of L, which is the upper sets, well, RC and RC generate their upper sets. But now if you take the upper set generated by the two elements R and C, it's also connected, RC and RC. So this should be, this is an extreme array which is not in the image of the unit embedding. So if you take this section that I talked about by the unit simplex, you get this kind of pictures. One is the upper sets and the other one is the lower sets. So you can imagine this kind of like very complicated polyhedra that you could get, well, you know, basically they're just cut out by these hyperplanes which are perpendicular to the roots EI minus EJ. But they're convex, and you can understand what's going on. Okay. All right. So let me say one last thing, or maybe the one before last, to be honest. Okay. So I said before that it's important for any construction to be sort of compatible with filtration, grading of texts. So it's a natural question to ask, what happens if you start with some text and then you add more texts, but without changing all the distances of the original ones? So in other words, if you have probabilistic language model L1 D1 is extended by an isometric embedding, okay, then is there an isometric embedding on the level of the presheaves? And the answer is there is one that respects the Yoneda embeddings. And moreover, what's more important, it's actually the smaller guy sits inside the bigger guy as the image of a retraction. In other words, a non-expansive min-plus projection. So you can control things. This is the formula. You can write down the explicit formula. This looks like a sum of one-dimensional projections here in this sense. But the interesting part is that now you can sort of use that because to project down to word space, because words is the shortest text. So the word space always lives in any kind of space you consider. And if you do that, if you compute this for words, in other words, you have some text B1, Bn, and W1, Wm are the words. So you can project in particular from the big space of this text to the space of these words. And then you get a sum over the Yoneda embeddings of the words, with coefficients being the distance from the word to the text for all words included in this text. Okay, so this is a min-plus sum. And now, as I was saying before, if you use the fact that the min-plus algebra is the limit of this guy, it means that if you take the exponential of this projection vector, that which you can think of this as the vector probabilities, it's a Boltzmann-weighted sum of the Yoneda embeddings of words. Okay, so naturally you get that, which is, if you've seen the transformer architecture, there's something called the attention layer. In the attention layer, the vector you find for a text is actually just such a Boltzmann-weighted sum of the vectors you find for words. So that fits the picture. Okay, and then the last thing I want to say is that there's a kind of mysterious object, which is, instead of taking now the min-plus span of the columns, you take the max-plus span of the columns. And this is extremely different because D is a min-plus idempotent, but it's not a max-plus idempotent. So this max-plus span, which is like saying from a categorical point of view that you take all limits, not all co-limits, all presheaves which are limits of representables. It's a highly non-convex space. It's a metric space in which the original finite metric space is also isometrically embedded. And in some way, it's kind of the smallest space you can fit this space in. And it has many names. It's called the Isbell completion, or it's called the tight span also in the metric literature. And we can show that this P of L, this nice convex space, is the lattice closure of this crazy but probably very, very interesting space. Yeah, so that's kind of the picture. And just to give some perspective, recently we had, by the way, I forgot to say that this picture about monoids, it came out of some joint work with Matthew Trager, which I mentioned from Amazon AI. So just to say the last word about perspective on this. Yeah, okay, so we discussed. By the way, yeah, let me point out that this space, which as I said is non-convex, but it's a polyhedral complex. It's kind of analogous to when you have a poset and you take the upper set completion. It's very simple, or the lower set completion is very simple, but it's big. There's a smaller one. And the smaller one, which is generalization of the Dedekind construction of the real numbers from the integers, is by taking cuts. So in other words, you take everything which is bigger than something, and then you take everything which is smaller than everything which is bigger. And if you come back to the same thing, then you keep that in your completion. Okay. So this crazy space is a generalization of that Dedekind completion. It's called the Dedekind-McNeil completion in the poset sense. So that's the interesting part of the story, which is still to be understood. Yeah, so let me just say one last word, maybe about meaning and about some indications. So we don't need that. Yeah. So from this point of view, it seems that this kind of space of presheaves somehow should be used to encode meaning. And there are several indications on that. One that I didn't mention is that actually you get a sort of logical structure. And when I say logical structure, I mean a Heyting algebra, not a Boolean algebra. A Heyting algebra has also and or negation, but the double negation is not equal to the original. So it's more general. And you do get, from limits, colimits, and inner home, you do get this kind of logical structure. At the same time, you know, the natural conjecture to make at this point is that because you can translate between languages, and if these pre-shift categories are the sort of encode somehow the meaning, then different languages should have equivalent pre-shift categories. This usually goes by the name of Morita equivalence. Okay, so one would expect that there is some sort of Morita equivalence. And in Morita equivalence, you can, if you have so-called Morita invariants. So things which, even though the categories look very different, they're Morita equivalent, and then there's some invariants. The invariants go by the name of, usually in algebra, Hochschild homology or cohomology. And now one may ask the question of how do you find something like that here? And there is a sort of proposal so to use something called magnitude homology. And there is some, which is actually kind of, magnitude homology is basically sort of metric space generalization of how one would construct, if you have a poset, you can take the nerve of the poset, and then you can construct a space and you can compute this homology. Well, there's a generalization of that in the metric case, and that's called magnitude homology. And soon, in the next couple of weeks, there will be a paper in the archive which shows that by Ty Bradley and Juan Pablo Vigneault. So Juan Pablo is in Caltech, and Ty works at a sort of machine learning company in California. And they calculated, they calculated basically that the Euler characteristic of this magnitude homology, they calculated at two levels. The first level is that of a number, and that number turns out to be the Shannon entropy. So the Shannon entropy appears from this game, and it's reasonable to expect that if you take big texts in one language and translate them in another language, that the Shannon entropy will be preserved, if the translation is good, at least. And there is a sort of a T, there's a sort of a generalization of Shannon entropy that depends on T, and which is called the Tallis entropy. And in this sense, this also appears there. But they'll put the paper out in a couple of weeks, so I don't want to say, and I didn't want to say anything more about that. So, but when this comes out, I think it will be also very interesting. Okay, so that's where I stop. Thank you very much.
Shannon entropy is a scalar?
Yeah, Shannon entropy is a scalar, yeah. Yeah, so the Euler characteristic is a scalar in general. And so that scalar turns out to be the Shannon entropy. Okay, yeah, but yeah, well, the Euler characteristic, but this function takes values in real numbers, so yeah, okay, so well, now I have to explain more. So basically, you end up having a formula which is a function of a variable q. So you have something with coefficients, something with a sub l, say, times q to the l, and then this q is e to the minus t. So what you get is something which depends on t. And then when you take an appropriate limit, you take that divided by t minus 1, then you go to the Shannon entropy. Okay. Yeah. So it's not a trivial calculation, but it definitely works. Yeah, okay. I can say also another thing. I mean, it's kind of related to Möbius inversion. It's a generalization of Möbius inversion, basically, where you do Möbius inversion for the zeta function of a poset. So the zeta function of a poset is a very simple matrix that just, you have the poset versus the poset, and you put 1 if AI is less than AJ, and you put 0 otherwise. And then the classical story says that you can invert this matrix. Its inverse is called the Möbius matrix. And then if you take the sum of the coefficients of the Möbius matrix, it turns out that this gives you the Euler characteristic of the nerve that you can get from this poset. So the poset defines for you a topological space. And then you can compute the Euler characteristic. And the Euler characteristic is that particular, turns out to be this comes from the Möbius inversion. Yeah. So yeah, it's not a trivial thing, but it definitely works. Yeah, I mean the paper will be out in a couple of weeks, so hopefully I can send you an email for that if you want.